Hi and welcome to Class 9. So we're at that stage where we're going to actually do a class that is very heavily influenced by some questions we asked way back at the beginning. In fact, before we recorded the first class, I was asking for ideas about things we were interested in. The thing that came up more than once was this idea of colour management. Can you give me insights in colour management, especially light management and how lights and stuff? It's basically that part of colour science where, for many people, that's the most, or probably the earliest point that they have serious contact with colour science because they're concerned about how they set stuff up and how this works. So that's this week, class, correct?
We'll talk about LUT math.
And that'll get us to a really good point for you guys. Now, of course, this is a changing area, so we're not going to be doing individual desks. We're not going to be like hauling in a bunch of different colour grading desks. So what we're talking about is what you would call, I guess, the deep theory and the maths behind it.
It's the maths behind how 3D lookup table interpolation, how it works.
Great.
It's time to talk about color transforms. We've talked about color science in the first few classes. We talked about grayscale mapping, perceptual uniformity. We've talked about video color space. We've talked about various different primary sets, various different RGB systems. We're headed toward the Academy Image Interchange Framework, which we'll talk about in Class 10. But meanwhile, we should fill in one missing gap, that of color transforms implemented with lookup tables. Or you could call it color management systems. That would be the terminology for desktop computing. The challenge is mapping one color space to another. And you've seen in many previous classes in this course mathematical equations describing transforms. And some of those equations are exactly appropriate for mapping between color systems that we would use in digital cinema or in HD, where we have a very simple mathematical model for the color mixing, additive mixing, for example. And also we know the color properties of the input and the output spaces. For example, from a particular color system associated with a set of spectral sensitivities in a camera to an interchange or coding space such as 709 or DCI P3 RGB. Any of those sorts of transforms can be accomplished mathematically, and we can turn the mathematics into FPGA code or C code or DSP or whatever circuits we need to implement them in real time. But we find as the needs for color and as the systems for mixing get more complicated, like the subtractive mixtures to mimic motion picture print film, the transforms are no longer linear. The transforms involve colors that are no longer an easily mathematically predictable mix between the two channels. And so we have a need for nonlinear mapping from one color system to another. And one way to implement such a mapping is by using a lookup table. And let's start this discussion by talking about a rather giant lookup table. For the sake of argument, we'll say 8-bit, 8-bit, 8-bit inputs. You can think of them as just being RGB. And addressing a table, each of those three coordinates, where we pull out a result from the table, and typically the result will be in a color system, so let's say 3 bytes in each table entry. So in the case of 8 bits, 8 bits, 8 bits, this could be RGB in, RGB out, but now the output system can be completely different than the input system. It can have different primaries, different tone curves. It can have nonlinear mixtures between the channels. Anything goes in terms of the result because you can load any number you want into each of those output cells. And at first glance, you think 8-bit, 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 256 cubed, 16.777 million. That's not so many. That's only 48 megabytes worth of table entry. That's not bad. Well, it's not bad for a desktop computer non-real time, but we're interested in color transforms that can be implemented in real time at HD or digital cinema pixel rates. And also we're interested in compact devices like cameras, where there's power limitations and space limitations, where 48 megabytes just for a single color transform is not practical. So let's then leave this full giant lookup table, 3D lookup table, in the back of our mind, but let's explore a different kind of color transform that's a little more general than just a 3x3 matrix mapping, but is a lot easier computationally than the giant lookup table. Instead of the giant lookup table, let's take a very small lookup table containing only 8 entries, corresponding to each of the 8 vertices of the cube. So think of this cube as going red on the vertical coordinate, green on the diagonal coordinate toward the back, and blue as the last coordinate corresponding to the horizontal direction. So for any particular 001, 100, any of those combinations just involving 0 and 1 coordinates, we just pick the result. But for all of the mixtures, what we do is take the amount of red between 0 and 1 and interpolate between these two outputs linearly. So the first step is interpolate 4 values which are intermediate corresponding to the red combination. Second step, interpolate across these pairs according to the amount of green to produce these 2 results. And as a final step, interpolate across those 2 according to the fraction of blue. So this interpolated result gives us the result mapping the input value corresponding to those coordinates. Now this approach gives you many more degrees of freedom than a 3x3 matrix multiply, but doesn't give you much freedom. It's only linearly interpolating across each of the 3 dimensions. So it's not able to incorporate nonlinear mixtures. Now, this is a very simple scheme computationally. It's a very small number of mathematical operations, but it doesn't encompass the full range of color mappings that we need in practice to address digital cinema or HD color transform requirements. Now, the solution to a practical, fast, reasonably simple mapping scheme was independently derived at by 3 or 4 people in the mid-1990s, even early 1990s, working on problems of color transform, not for motion images, but for still images in graphic arts. And the solution involves mixing the best properties of each of those approaches that I've just explained to you. The solution is start with 3D LUT interpolation, but not a giant LUT. Instead, a modest-sized LUT. And for this example, I'd like you to think of R, G, and B being only about 4 bits each. Now, some people think it would be convenient to use numbers running 0 to 16. And it doesn't really matter whether you run 0 to 15 or 0 to 16. Some people like 16 cubed as the size of this table. Most people prefer 17 cubed. 17 cubed is 4,917. That turns out to be a very good match to the nonlinear mixtures and nonlinear transforms required in many practical situations, even subtractive mixing. So in essence, you can think of taking 8-bit RGB in, stripping off the top 4 bits of each. That would give you the 0 to 15 mapping. Using that 4-bit, 4-bit, 4-bit map to pull a table entry out, which then has got the output color values corresponding to that input combination. Well, if you just had 4 bits worth of red, green, and blue, obviously that's going to contour like crazy. So to avoid contouring, we simply linearly interpolate within each of those small lattice cells. And there's 5,000 of those cells. Generally speaking, the color transforms that we need to implement are smooth enough that linearly interpolating across each cell is perfectly smooth in practice, or I should say smooth enough. So we take 4,917 lattice points, or I should say lattice cubes, each with 8 points, 8 vertices, and in that little tiny cube we do exactly the trilinear interpolation that I showed you a moment ago. So here's a solution by which we take 8-bit, 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 split it into the MSBs and the LSBs, use the MSBs to access the table, use the LSBs to interpolate in the lattice subcube. Now, as I mentioned a few moments ago, this scheme was invented for graphic arts, basically invented for offset printing and inkjet printing. That scheme wrapped up in a specification of how to represent the table in a file, how to represent the auxiliary information, where to put things like the white point and the device name, and you could call it metadata. All of that data is wrapped up. That forms an ICC profile. The organization that standardized that scheme is the International Color Consortium, ICC. That's how desktop color management happens for offset printing, inkjet printers, and even some digital still photographers are using the ICC architecture and the ICC files to do their color mapping. It turns out that the ICC architecture as a whole is built on an assumption which breaks for digital cinema. And the assumption is this: in graphic arts, white is always as white as you get. In graphic arts, you cannot get whiter than a white piece of paper. Basically, no account is taken of specular reflections which reach luminance levels considerably above the reflectance of the paper. But in cinema, we do that all the time. So that's the main conceptual reason that the ICC framework, taken literally, doesn't really work for the movies. However, the basic architecture of the table interpolation does work. And so versions of this scheme, but not according to the ICC standard, are used all the time in digital cinema. Now, we can make a few simplifications to those computations that make things easier and faster and even perform a little better. The first observation is we can take each lattice cube and split it into 2 prisms. Now, this isn't the Newton's prism we were using the other day. By prism, I'm just referring to this 5-sided figure where we break across one of the diagonals of the cube. And the advantage of doing so is that when we do a color lookup, instead of having to access 8 triplets from our color profile memory, from our mapping memory, we only have to access 6 triplets by simply determining which side of the major diagonal are we on. And there are people who implemented that arithmetic directly by simply comparing 2 coordinates, figuring out which prism we're in, and then accessing the 6 vertices of that prism, doing the arithmetic with 6 numbers instead of 8. But we can go one step further. We can do a little further comparison operations to take each prism and split it into 3 tetrahedra. So the 2 prism slices would then be 6 tetrahedra. And now by doing a few comparison operations to see in which space we lie, now we require only 4 lookups to get the data that we need to interpolate. 1, 2, 3, 4. We still do the same tetrahedral interpolation, or there's another variation of the math called barycentric interpolation. But in any event, the table is constructed identically no matter which of these schemes you use. These are just implementation schemes at the bottom end of doing the color transforms through a 3D interpolated LUT. So we start with the subcube in cubic form, we break it into 6 tetrahedra, and we interpolate based on that. Now, I'll borrow a drawing here from Steve Edens, who's basically Mr. Image Processing Toolbox of MATLAB, and he made these drawings because he was exploring color space conversion. And so he's showing you a drawing of the full cube from 0 to 1, so these are like fractional coordinates now. And he breaks them apart and shows you how to determine which of these 6 tetrahedra you're located in. That tells you how to do the interpolation. And the interpolation looks something like this. This is a half a page of code that I've taken from a document posted to the web by Filmlight. And code like this presumably lurks at the bottom of the TrueLight color calibration package. And this code was written by the madman color scientist of Filmlight. His name is Richard Kirk. So you can see that the bottom end of the color transform, the 3D lookup table interpolation, it's just a bunch of multiplies and adds and compares. So there's work, there's number crunching to be done, but it's reasonably simple. And this 3D interpolated LUT scheme has proven to be highly practical, not only in the ICC formulation, which is used for desktop computer graphics and graphic arts, but also in a somewhat modified or extended form used all over the place in digital cinema. This is the basis of 3D LUT interpolation. Now, we haven't yet discussed how you get the numbers that go into the table, and that's a bit of a tricky part. We do that in a minute. Before we do that, you realize that from transforming to one color system to another color system, say the color system associated with one device into the color system associated with another device, if you had n input devices possible and m output devices, that would be an m times n problem. If you look at what we examined in the first few classes of this course, you realize that we could use the big X, big Y, big Z standard color space as an interchange medium between spaces of different flavors. So mapped into the 3D lookup table interpolation scenario, you can think if we just take all of our n input devices and build transforms into XYZ, and then take all of our m output devices and build transforms from XYZ into those m different devices, that's now an m plus n problem. And m plus n is generally quite a bit smaller than m times n. So we use this idea of having a conversion space, building transforms into the common conversion space, and building output transforms out of that space. And in the ICC color management terminology, that's called a profile connection space. The mapping from a device into standard space is an input profile. At its heart, it's just exactly that table of numbers that executes the 3D interpolated LUT. And for each output device, we build an output profile that goes from the standard space, or in ICC terms, the profile connection space, into the output device values. Now, in motion picture work, we don't really talk about profiles so much, and we don't use the term profile connection space, but the fundamental operation is very much the same. Now, in the early days of the ICC, the profile connection space was an 8-bit space, and as you know, linear light 8-bit doesn't work in practice for reasonable contrast ratios. So the first instantiation of ICC used 8-bit L star, A star, B star coding. The next version of ICC extended the arithmetic to 16 bits, and that enabled use of big X, big Y, big Z linear light tristimulus values. So in today's ICC world, you've got the possibility of both. Now, we still face the question, how do you get the numbers that go into the tables? And I'm giving you an example here of a test target that's used in the printing and publishing business. And it's recorded onto paper or recorded onto film, and then the patches are measured. Now, you might think, well, we'll just use a Macbeth, or what I would prefer to call a color checker, but 24 patches really isn't enough to build a good color mapping. So something like the 228 patches of an IT8 is a better move. And in practice, in digital cinema, there's not yet at least, any standardized patterns. So in the example of building a profile for an input device, we use this pattern. We do two things. We measure the patches with a color measuring instrument, and then we use our input device to report device values corresponding to each patch. Now we've got a set of color measurements and a set of device measurements for the same patch, times 228 patches, or as whatever number you choose to use. But that correspondence allows us to build the transform mapping from one to the other. So to use a very crude sketch made on the back of a napkin, we shoot the calibration target with our camera to get device values. We measure each of these patches with a color measuring instrument to get colorimetric data. Now we've got a set of colorimetric triplets and a set of device triplets. The building of the table is just mapping all of those 228 associations to the right places. Now, it turns out, and I'm not going to spend a lot of time on this, but it turns out that if you make the target so that it has relatively evenly spaced color measurement values, then the task of building the profile in the input mapping profile, its job is to take device values, and they're equally spaced, carved into, let's say for the sake of argument, 16 bins on each of the three axes. So if you start with equally spaced color measurements, the device measurements are not going to be equally spaced. The big mathematical problem of building the table is inverting the mapping to deliver a table that's equally spaced in device values, even though the color samples aren't equally spaced. Now, if you didn't get all of that, don't worry about it. I'm not expecting any of you to have to actually write the code to build those tables, because that code is already written in the form of color calibration packages, of which I've already mentioned TrueLight as being a very good example. So TrueLight or other color calibration packages build the table for you based on scans and color measurements that you make. Now, on the output side, it turns out to be basically an identical problem computationally, though now we start by having synthetic data, device values that we write out through our output device. And I guess I should apologize here that this is an old slide on the back of a napkin, and I'm showing this like it's a printer onto paper. But for our purposes, we'll either want to record film and measure that, or put up color patches on a display and measure those. We do those measurements with some sort of color measurement instrument that delivers triples that we measure. We get this triples from the device values that we shipped into our output device. That allows us to build a color transform corresponding to the output device. Now, to do the measurements on film is not easy. Here's a machine built by my colleague and friend Joseph Goldstone, who built this literally or figuratively in his garage out of Lego. And he's no longer on his own. He works for ARRI now. And this machine is a wonderful example of do-it-yourself color measurement. And several participants in the digital cinema revolution have been using measurement data derived from machines like this to build transforms to go from digital data to film data, or from film original camera negative, characterizing the front end, characterizing the back end. Now, just to fold this topic back to the beginning of the class, I was talking about the adjustments necessary in the image data to go from a certain kind of absolute luminance level in a scene to the 48 nit peak luminance or 24 nit typical diffuse white luminance found in the cinema. And when you measure original camera negative film on a construction like this, and you measure print film on a construction like this, you find that built into the chemistry of the film is a transform that accomplishes that basic picture rendering, that adjustment of color values to make the picture look right. And we will be exploring that further in the next class, where the Academy Image Interchange Framework participants have been working for several years to identify a mathematical form of that transform that film has been doing chemically for the last 30 or 40 years. And that Academy transform, I think, forms the current state-of-the-art, or soon-to-be current state-of-the-art, in mapping film data from the camera to the film screen. So we'll see you next class when we talk about that topic.
Okay, Charles, so that's got us to a point where you said at the outset of this was Class 9, pretty much based on a whole bunch of questions we got for things that we'd like you to cover in the course. Mm-hmm. Next class, if you like, is the stuff I'd like you to cover in this course. In fact, obviously I've been following Charles' stuff for many years, reading your stuff, but the reason I called Charles, whenever it was, 6 months ago, to start this current ball rolling was over this very next topic, which we'll be covering in week 10, which is?
Which is the Academy Image Interchange Framework and its associated color encoding specification and reference rendering transform, all of the Academy work.
And this is very, very current. I mean, that's where we're recording.
Very current, and I consider it to be kind of the today's ending point of all of that theory and practice that we've talked about in the previous 9 classes.
Yeah, this is really important stuff. We've covered it a little bit in background, but this wasn't obviously at a 300 level, it's at a 200 level, so I'm really looking forward to this. And I believe, I'm not going to say, but I believe you're going to approach it slightly differently than you've approached any of the lectures up until date. So I look forward to finding out how that's going to play, and that's next week in Class 10.